Hello, everyone, and thank you for choosing this webinar. My name is Eileen Peppard, and I work for Sea Grant Center for Smart Building and Community Design at the University of Hawaii, Manoa. I also work closely with the School of Architecture. This webinar is a recording of a workshop conducted in June of 2021. We have not included recordings of the breakout session discussions, but we do include the summaries the group moderators provided afterwards. Throughout this webinar, you'll be asked to pause the video and respond to survey questions. Please keep the survey open because you will continue to return to it. The link to the survey is in the description below the YouTube video. Your responses are anonymous and participation is voluntary, but for those of you who would like to earn AIA credits, participation in the survey is required and you'll be asked to provide your AIA number at the end of the survey. When you reach the end of the survey, please be sure to hit the submit button. Mahalo.
Welcome, everyone, and thanks for being here. Get the slides started, and thank you so much for joining our workshop today. The workshop today is hosted by the University of Hawaii, and it is on the research project entitled Envisioning In Situ Sea Level Rise Adaptation Strategies for a Densely Developed Coastal Community, Waikiki. A quick introduction to our team. Our workshop today is hosted by an interdisciplinary team from the University of Hawaii School of Architecture and School of Ocean and Earth Science and Technology. It includes myself, Wendy Megoro, Professor and Associate Dean Chip Fletcher, Hawaii Sea Grants Eileen Peppard and Dolan Eversole, and graduate research assistants and Doctor of Architecture candidates Jojo Briones and Ireland Castillo. Next slide, please. We're hosting this, just so you know, we're hosting this workshop multiple times with a diverse set of stakeholders with relationships to Waikiki in order to facilitate discussion in small breakout groups. Next slide, please. And first, I'll give a little bit of background on this research project. With sea level rise, densely urban Waikiki will need an in-place or in-situ adaptation strategy, which has yet to be defined and envisioned. So the UHC Grant and School of Architecture are working on a research project to create conceptual design renderings and a written design brief to help visualize preliminary flood adaptation strategies in Waikiki. And the goal for this workshop is to present example sea level rise adaptation strategies and seek your feedback on their applicability to Waikiki. And your feedback will inform the future conceptual design renderings. During this workshop, we will first survey your impressions about sea level rise, both before and after the workshop to gauge if they change. Then we'll describe the sea level rise science and its planning implications. Afterward, we will present flood adaptation strategies that we think are relevant for Waikiki in the categories of buildings, open spaces, transportation, and utilities, and we'll collect your feedback via survey along the way. Then after a short break, we will create breakout groups to gather your thoughts on those flood adaptation strategies. And finally, we will have a short summary at the end, a final survey, and conclude by 11 a.m. Next slide, please. And to give you a little bit of background on where this workshop fits into the larger 2-year research project, first, faculty and students conducted background research, learning from emerging design, flood resilience standards and guides, case studies, and flood hazard maps. We identified the flood adaptation strategies that seem relevant for Waikiki, which we'll share and solicit your feedback on today. Next, students will create site-specific urban and architectural renderings of a habitable, attractive, economically vibrant Waikiki with flood adaptation strategies. And finally, we will again meet with stakeholders to review and provide feedback on those draft renderings before revising and publicly sharing them. And the goal of the renderings is to contribute to design guides, educational presentations, pilot projects, and new policies or incentives that prepare for future flooding. Next slide, please. And so we're on the same page when I say renderings or diagrams. Here are some examples so we have a common understanding of those terms. We'll return to these at the end of the presentation.
Thanks, Wendy. Hello, everyone. We are transitioning to our first survey questions. If you haven't opened it yet, you can find the link to this in the description below the YouTube video. Again, your responses are anonymous, and we really appreciate your feedback. Remember, keep the survey open because we go back and forth from the video to the survey. Mahalo, everyone.
So next up, Professor Chip Fletcher is going to brief us on the latest sea level trends, science, and forecasts.
Hi, folks. Good to see everybody this morning. Let me share my screen. And we're going to just go through a little briefing, 10 to 15 minute briefing on climate change, sea level rise specifically. So the causes of global mean sea level rise include the melting of mountain glaciers, roughly 1/5 of the total contributions to global sea level rise. Another 1/5 coming from the melting of the Greenland ice sheet, about 10% from Antarctica, the glacier, the continental glacier located there. And during the course of the 20th century, we were busy damming rivers and building reservoirs and basically preventing water from flowing into the ocean. This actually slowed down sea level rise until most of the reservoirs and rivers, major rivers of the world now have, that activity has been completed. And now when we pull water out of the ground, largely for irrigation and agriculture, it flows into the sea, whereas previously it was in the crust. So as a result of this, we now see that reservoirs and groundwater depletion actually is a contribution of about 10% to global mean sea level rise. And of course, as the ocean comes into equilibrium with the temperature of the atmosphere, that heat transfer into the ocean causes it to thermally expand. And this is the major component of today's global mean sea level rise, about 38%. So let's establish some conceptual foundation at this point. Sea level has risen 8 inches since the 19th century. And as you can see from the background photo, the impacts are already upon us. Everything scientific research has told us about future sea level rise tells us it will be many feet higher, rising much faster, and is unstoppable unless air temperature is lowered to pre-industrial levels. The ocean will take many, many centuries, in fact, beyond 1,000 years, to fully equilibrate water temperature with air temperature. And in so doing, it will continually thermally expand, even if we stop global warming, and even if we begin to pull CO2 out of the atmosphere. It's been said that we need to lower atmospheric temperature to pre-industrial standards in order to get the ocean to stop thermally expanding. Hence, as Michael Oppenheimer, lead author of the 2019 IPCC report on sea level rise, says, there is no scenario that stops sea level rise this century. We've got to deal with this indefinitely. So we measure sea level rise beginning in 1992 with a series of satellite altimetry missions. First was TOPEX Poseidon, and then JASON's 1, 2, and 3. These are combined missions with the European Space Agency and NASA. Here you can see the data from each of these missions. The long-term rate from the beginning of the time series in 1993 is a little over 1 foot per century. But in the last decade, it's accelerated and it is rising at a rate of about 1.5 feet per century. And the current rate of acceleration of this time series would put it at a little over 2 feet by the end of this century. Now, the author of this information is Steve Neeram, and he published a report in 2018 extrapolating or extending the rate of acceleration. And he commented that our extrapolation assumes that sea level continues to change in the future as it has over the last 25 years. Given the large changes we're seeing in the ice sheets today, that's not likely. And what he's indicating is that 2.1 feet as an estimate of global mean sea level rise by the end of the century is probably an underestimate. So in 2020, the temperature of the oceans set a record for heat storage from the atmosphere. And as I've mentioned, it'll take over 1,000 years for the ocean to come into equilibrium with the air temperature. And this entire process will lead to continued thermal expansion. Greenland is melting. The rate of mass loss from Greenland has quadrupled in the past decade. Researchers have stated that the Greenland ice sheet discharge into the ocean is far surpassing snow accumulation, and the entire ice sheet is in a constant state of loss. Even if climate change stopped, the ice sheet would still be losing mass. Antarctic mass loss has tripled since 2010, especially this dark area where we have a number of ice streams flowing into the ocean in West Antarctica. Especially dangerous are the Pine Island Glacier and Thwaites glaciers, both shown here. This short video, especially over here in this window P2, accompanied a research paper that describes new disintegration of the floating ice shelves for Pine Island Glacier and Thwaites Glacier, showing these tensional fractures or rip-away fractures as the flow into the ocean accelerates. These are the first signs of structural weakening and precondition these ice shelves for disintegration. It's these ice shelves that buffer or hold back the main body of ice in West Antarctica. And when we see these ice shelves rapidly disintegrate, we worry about rapid ice flow into the ocean and the potential for multi-meter sea level rise this century. We also have ice centers in many of the world's mountain systems. In every case, the total amount of ice in the major mountain systems is in retreat, and the mass loss combined into the ocean is about 280 billion tons per year. That's roughly equivalent to the amount of mass being lost off of Greenland. And our understanding of all the components of sea level rise have led to a number of projections. The Intergovernmental Panel on Climate Change, most recently in 2019, projected global mean sea level rise of 3 to 4 feet by the end of the century if we are successful in stopping warming at about 2 degrees Celsius above pre-industrial temperatures. If we are not successful in that, then we face the prospect of multi-meter sea level rise late this century. Now, global sea level rise and local sea level rise can be very different. And one of the main reasons for this is known as sea level fingerprinting. So if we have an ice body such as Greenland or portions of Antarctica that loses mass, its gravitational field decreases. And that gravitational field today is actually pulling seawater towards it. And as that field decays, seawater will flow away. And in the far field, we will see a compensating sea level rise, which is greater than the global mean, because here at the place where the gravity field is lost, we will see sea level that is less than the global mean rise. And unfortunately, Hawaii lies in the far field of all the major ice centers. The Greenland ice sheet, you can see as the gravity field there decays, we actually have sea level fall specifically related to that process in the North Atlantic. But here in Hawaii, we are in the worst location for the sea level fingerprint process. Likewise, in West Antarctica, East Antarctica, and the median solution for the world's mountain glacier systems. The result is, if the global mean rise is projected to be 1 meter by the end of the century, we would see another 30%, or about 1.3 meters. Likewise, this common number of 3.2 feet by the end of the century would be actually 4.3 feet in Hawaii, or at least at the Honolulu tide gauge. Now, because there is no model that encapsulates all of these physical processes together, NOAA has provided planners with 6 scenarios on which to base their community planning. The lowest 2 scenarios here, the low and intermediate low, do not reach that 2.1 feet of sea level rise by the end of the century that the current global mean acceleration would reach. And so we're going to discount these 2 lowest scenarios. That leaves us with the NOAA intermediate scenario of about 1 meter for planning purposes by the end of the century. And depending on the risk tolerance of a planner's project and the high uncertainty, especially of the West Antarctic ice sheet, a choice can be made for some of these higher scenarios, especially this, what's known as the extreme scenario of 2.5 meters or over 8 feet by the end of the century, for projects with a very low tolerance for risk. NOAA also provides decadal projections for these different scenarios. You see on the left side, intermediate, intermediate high, etc. And then here are the decades in the future. I've highlighted the intermediate scenario and the end of the century. The global mean sea level rise would be 3.3 feet, but at the Honolulu tide station, because of sea level fingerprinting and other localized processes, 4.3 feet. But we are familiar with the fact that sea level has already entered our neighborhoods in the form of king tides. Extreme tide flooding arrives decades ahead of this exponentially rising permanent inundation curve. And as we get closer and closer to the permanent inundation of this black line, we see accelerations in the frequency and magnitude of this king tide flooding. And all of that is modulated by gravity processes associated with our proximity to the moon and sun as we move forward. And this has most recently been published by Phil Thompson and his team at the Hawaii Sea Level Rise Center. What does sea level rise look like as it enters our communities? We see storm drain backflow. We see flooding from the drainage system. Here we're on the left side, we're looking at Waikiki, and on the right side, we're looking at Mapunapuna. These are what extreme tide flooding looks like. We also know that the water table moves in coordination with the ocean tides. And so as the ocean rises, the water table beneath the land will rise. In Waikiki, we only need 2 feet of sea level rise before we see dry land turning to wetlands at the high tides. If we combine this groundwater inundation and the storm drain backflow with an intense rainfall event, we end up with flooding because there's no place for runoff to go. There's no drainage capacity. Dr. Shelley Habel of the UHC grant program modeled all of these processes in her PhD project. And here you see one model result for sea level rise of 1 foot above present. Purple indicates where there is groundwater flooding. Green will indicate storm drain backflow, and blue indicates direct marine flooding across the shoreline. And these pink dots indicate where individual storm drains are blocked by high seawater. So here is 1 foot of sea level rise, 2, 3, and you start to see these red lines. This is 4 feet. So this is projected for the local sea level rise by the end of the century using sea level fingerprinting. These red lines indicate that we have exceeded the transportation engineering threshold of 6 inches of standing water, where a small vehicle driving through that will create a bow wave that comes back into the engine compartment and potentially stalls the vehicle. And this would basically shut down a street as a option for automobile transportation. There is 5 feet. So let's summarize. West Antarctic glaciers are the current greatest source of future sea level rise uncertainty. The science is still unsettled. Planning in general should be risk averse, and the Honolulu Climate Change Commission recommends establishing this area to be flooded under 3.2 feet, which is very roughly 1 meter, as a planning benchmark by the end of the century. High tide flooding will arrive decades earlier in that area. And global emissions and amplifying feedbacks are currently projected to cause about 3 degrees Celsius of global warming. I didn't get a chance to go into that, but this is a conclusion that's widely accepted. Critical infrastructure projects with long expected lifespans and low risk tolerance because of this should set 6 feet at least as a sea level rise planning benchmark. And the area experiencing or that is mapped as exposed to 6 feet of sea level rise will experience chronic high tide flooding decades ahead of permanent inundation. And so we should consider about 1 meter as a minimum, and projects can use the NOAA sea level rise scenarios, picking the scenario that best fits the budget, timeline, and risk tolerance. And I'll end with that. Thanks very much. Back to you.
Thank you, Chip. So now that we know a little bit more about the sea level rise science and the implications of the temporary or permanent inundation or flooding, next we're going to go over some potential flood adaptation strategies that we think are appropriate for Waikiki. These will be presented by our graduate research assistants, Ireland Castillo and Jojo Briones.
Good morning, my name is Ireland Castillo, and today we'll be looking at adaptation strategies related to buildings, open spaces, transportation, and utilities. Some terms and conditions that we'll be using throughout the presentation include the terms protect, accommodate, and avoid. Adopted by the American Institute of Architects, or AIA, we've categorized the following strategies based on these definitions. For in-place flood adaptation Waikiki, we've identified strategies that protect or accommodate. Some terms you may be all familiar with and which we'll be using throughout our presentation include the terms base flood elevation, or BFE, design flood elevation, or DFE, and freeboard. The diagram being shown to the right is adopted from the Boston Coastal Flood Resilience Design Guidelines, showing the relationship that the BFE, DFE, and freeboard share. A common question that we get that is asked is how much freeboard is appropriate and what standards/codes to follow. Different standards and guides recommend varying amounts of freeboard and future sea level rise as shown in this chart. The amount of freeboard often varies based on building class, criticality, and/or risk. Honolulu has adopted the 2012 International Building Code, and this requires that new construction be designed with 1 foot of freeboard above current base flood elevation levels in hazardous flood zones, according to AAC standards. For our project, we align ourselves to the codes and standards enforced by the city, and suggest creating new design flood elevations that account for building criticality, lifetime, and risk. And in order to identify appropriate flood adaptation strategies, we first surveyed flood resilience standards, guides, and case study projects as listed here. The ideas presented today align with Honolulu's climate adaptation design principles for urban development.
Thanks, Ireland. My name is Jojo, and as mentioned earlier, in the following slides, we'll review various flood adaptation strategies and discuss how they'll be applied to the buildings, open spaces, transportation, and utilities in Waikiki. And we'll be asking for your feedback in between. Most of the examples refer to adaptations of existing buildings, but the principles may also be applied to new building design. And starting off, we'll jump into buildings. Next slide, please. Specifically, we'll look into the strategies to protect from or accommodate flooding for buildings in Waikiki. Next slide. The first strategy is to elevate buildings above the design flood elevation, either on an open foundation, like in this diagram. Next slide. Or elevating on fill. Next slide, please. And another protection strategy would be to dry floodproof by making a structure watertight below the level that needs flood protection. This is appropriate for non-residential buildings. Next slide. And then moving on to relocation, strategies include reevaluating spaces below the DFE to become non-occupied uses or to be filled. Next slide. As well as relocating those critical systems above the DFE. Next slide. And then for accommodation strategies, they include wet floodproofing, which allows the water to enter into the space. And the next slide. As well as building with flood resistant materials. Next slide, please. So we'll illustrate next how these flood adaptations might be applied to a typical existing building condition in Waikiki with below grade, at grade, or above grade occupied spaces, and then solicit your feedback. Next slide. First, we'll go through the below grade occupied spaces and or parking. Next slide, please. So these images shown on the top, which is a below grade parking, and then there's an image that shows below grade occupied space on the bottom. Next slide. And then in this diagram, we've highlighted areas that represent the building openings that are at risk for flooding, and the arrows depict the potential flow of water that would enter into these spaces. Next slide. And in the below grade spaces, we propose to prioritize the actions of first relocating critical systems to wet floodproof and then build with resistant materials. And then if possible to reevaluate those spaces entirely to be that are below the DFE. Next slide, please. On the next few slides, we'll reference these diagrams that are from Boston Coastal Flood Resilience Guidelines, and on the left is their diagrams, and then the photos on the right are the actions in practice. So the top right photo shows how to raise a critical system that is above the DFE on a platform for a detached dwelling. Next slide. And then this diagram on the bottom left, and then the photo on the right shows a wet floodproofing, where the building has flood vents that allow the water to flow freely in and out of the flooded space to help reduce or equalize the hydrostatic pressure that could otherwise severely damage the building. And as a fact, the wet floodproofing is a strategy that is built into the City and County of Honolulu revised ordinances. Next slide. So spaces below the DFE also can be built to be flood resistant with flood resistant materials, and FEMA lists acceptable materials and their applications as well as unacceptable materials. Next slide. And then lastly, when reevaluating spaces below the DFE, previously occupied spaces should be filled to the lowest adjacent grade and converted to non-habitable spaces, such as storage. And the Boston guidelines suggest recuperating those lost square footages with new addition to a top top floor of the existing building, as shown in this photo on the right. And then the bottom image depicts a parking garage that is in the Netherlands that is used for temporary water storage in the case of a large rainfall event. Next slide, please. And then we'll move on to at-grade occupied spaces. Next slide. So Waikiki has many examples of commercial and residential buildings with openings at grade. Next slide. Although these diagrams are not to scale, they show that in the future, the buildings may have a design flood elevation that's higher than the existing ground floor and will present potential ways to increase the height of that ground floor. Next slide, please. So the at-grade spaces could utilize strategies we mentioned previously. And in addition to dry flood proofing and elevating the lowest interior floor with interior or exterior access to the DFE. Next slide, please. So dry flood proofing makes a structure watertight that is below the level that needs flood protection. And this photo on the right is an example of Whitney Museum in New York City with temporary flood barriers that are deployed in anticipation of a major flood event. Next slide. And the next strategies are to elevate the lowest level interior floor with exterior access to the DFE. The top right shows a photo of the newly constructed Whole Foods in Ward Village, and it shows how the elevating the lowest interior with exterior access, as well as an elevated sidewalk. Next slide. And then alternatively, we can elevate the lowest interior floor with interior access to the DFE. And that's shown here in the bottom photos with an example with interior stairs to an elevated interior floor, both in Waikiki and also in Venice, Italy. Next slide, please. So last, we'll move on to above grade occupied spaces. Next slide. And these two photos here represent some typical conditions we see in Waikiki of a low-rise residential walk-up and a high-rise apartment complex or hotel. Next slide. And again, although this is a representation of the BFE and DFE that are not to scale, it seems likely that the occupied spaces may already be above the DFE. Next slide. So these buildings that are already elevated on an open foundation or elevated on a fill and might have the actions for the future of relocating critical systems, or number two, which might be re-evaluating spaces below the DFE if they have any. Next slide, please. And as stated in the Boston Design Guidelines, existing or new buildings elevated on an open foundation must be designed to structurally resist the design flood loads and geotechnically stable and protect from erosion. Then once flooding becomes frequent, parking would likely be relocated. Next slide. So existing buildings that may already be elevated on fill should be compared to future proposed design flood elevations. And lastly, new buildings would likely be elevated on structural fill to meet the DFE. And now I'll pass it to Eileen for a short survey on the previous slides we just talked about.
The next part of the survey will ask you for your feedback on the strategies that were just presented.
Next, we'll be going over adaptation strategies related to open spaces. And as Chip mentioned, as the groundwater table rises and storm drains back up in Waikiki, rainfall may not easily infiltrate into the ground or be quickly drained to storm sewers. So in our case, we've proposed strategies to modify existing open spaces in Waikiki to encourage the collection, temporary detention, and filtration of runoff from large rainfall events. Proposed strategies include cisterns and water collection, floodable open spaces, and what we've termed ecological water treatment. The strategies presented apply to new and/or existing open spaces, including landscaped areas and/or parks, parking areas, and existing vacant lots. We will illustrate the following strategies through the following three case studies. First, buildings and landscapes may be designed to direct rain and stormwater runoff to to cisterns for non-potable use or for delayed discharge to the storm sewer. This aligns with Honolulu's One Water for Climate Resiliency white paper and has potential co-benefits such as reduced potable water use. In addition to our discussion of cisterns and water collection, we're also interested in the design and use of green and blue roofs. In this example, Olakaʻilima Art Space Loft is a great local example of multiple detention tanks being used to store rainwater while tastefully incorporated in the design of this communal courtyard. Our second case study shows floodable open spaces where, as outlined in blue, the basins at Water Square Bethlehem in Rotterdam, Netherlands, may provide public amphitheater seating when dry, and when wet, hold water for delayed discharge during large rainfall events. Lastly, Tanner Springs Park in Portland, Oregon exemplifies ecological water treatment. This urban park receives stormwater runoff from the entire block, where it is filtered and cleansed in a constructed wetland. This creates habitat while creating a park-like setting for the public to enjoy. Similarly, we'll go through another set of questions related to these strategies.
The next part of the survey will ask you for your feedback on the strategies that were just presented.
In this section, we'll discuss transportation and its related strategies. Next slide. So this section diagram illustrates potential flood adaptation strategies for transportation. It includes elevating the streets and sidewalks on fill, creating resilient streetscapes, transition zones, and accommodating walking and biking. These reflect the priorities in the Honolulu Climate Adaptation Design Guidelines and the Complete Streets goals. Next slide, please. In an effort to identify transportation ways that need to elevate first, this map highlights the major vehicle, bus, and bike routes. Our next steps will be to overlay 3.2 foot of sea level rise, exposure area, and map streets where groundwater is just below the surface causing instability, and identify emergency vehicle and evacuation routes. Next slide, please. We'll consider how transportation ways may be transformed to be resilient for future flooding. Next slide, please. And we've chosen to highlight these two case studies that are located in Miami and Honolulu. Next slide. This first case study is in Purdy Avenue in Miami, Florida, showing the adapted elevated street on the left and flooded before condition that's highlighted in blue. Some of the roads were raised as much as 2.5 feet, and that's higher than their original elevation of 1.2 feet. Next slide, please. And then this image on the right, now highlighted in blue, shows the street after it's been elevated on fill. Next slide, please. This case study, which was built in 2016, shows raised walkways and resilient streetscapes, transition zones here in Honolulu at the Ward Village South Shore Market. And here the pedestrian zone is emphasized. The trees provide shade and a planter strip separates the road and the sidewalk. And again, I'll pass it to Eileen for a survey.
The next part of the survey will ask you for your feedback on the strategies that were just presented.
Lastly, we will be looking into adaptation strategies related to utilities. Continuing our discussion on the topic of raising the street on fill, we've looked into specific strategies like 1, relocating critical equipment, 2, protecting and replacing city utilities by relocating them within the proposed fill and creating vaults, and lastly, incorporating some type of potential below-grade stormwater sewage within the proposed fill. We are considering how utilities, including electricity, water, sewer, gas, telecommunications, can be resilient in the future of sea level rise. We'll describe 2 case studies applicable to Waikiki. A good local example of what elevating critical equipment could look like can be seen on Queen Street, right behind South Shore Market. Here, elevate on some type of concrete platform. Utilities may also be protected from flooding if placed in vaults, as outlined in blue, in Aero and D-Land Studios' speculative project for the Museum of Modern Art exhibition, Rising Currents, Projects for New York's Waterfront, they had proposed this idea as well. Honolulu's Climate Adaptation Design Guide also illustrates utility vaults placed beneath the streetscape transition zone. And as we raise the streets, we see an opportunity to provide some type of below-grade water storage in the new proposed fill. The cisterns would temporarily detain stormwater in a large rainfall event and be pumped out afterwards. And for these strategies, we'll go through one survey, some similar survey questions.
The next part of the survey will ask you for your feedback on the strategies that were just presented.
So the next set of slides are intended to give you an idea of the renderings that we are envisioning. And next slide, please. These ones were created by student Kaimana Tuazon in the graduate elective course at UH. So here, the existing conditions you might see include the alawai on the right-hand side and the existing streetscape and sidewalk. Next slide, please. When we start thinking about 3 feet of sea level rise, some potential design strategies might include elevating the sidewalks on either side, providing that resilient transition zone with vegetation, elevating utilities below grade, and then providing a cistern below grade in order to temporarily hold stormwater. Next slide, please. And we want to think in this project over time how we might continue to adapt. So projecting forward to 6 feet of sea level rise, here you see further elevation of sidewalks and bike lanes. Vehicular transport is limited now to 1 lane for public transport and emergency vehicles. And other modes of transportation are emphasized, like the rail or boat transportation. Next slide, please. And all of these strategies can also be seen on a building scale. So one existing condition that we encounter in Waikiki are below grade spaces that are below the base flood elevation or a future design flood elevation. Next slide, please. So potential strategies include filling that below grade space, elevating the sidewalk, including elevating utilities, and considering the transitions between the street, the sidewalk, and the building. Next slide, please. And all of those elements come together in more lifelike renderings. And those renderings can depict different scenarios of adaptation strategies over time and help to coordinate discussion between multiple groups and give feedback on the feasibility, phasing, and benefits or concerns with these types of strategies. So again, these are student preliminary renderings. Our next step in this research project is to create other renderings, and we're incorporating your feedback on those. Next slide, please. I'd like to go around the room and have the facilitators share a short tidbit, a quick glimpse into their breakout discussion. So I will begin, and it sounds like it might piggyback off of what was just being discussed. We were talking about dealing with, I think one of the things that we're grappling with are those lower below grade spaces and what to do with them when the water is starting to come in. Should they be filled? Should that water be pumped out? And I think some of those pumping strategies are being used, and some of the questions that we had with regard to future fill would be, what is the quality of that fill? Does it contain any contaminants? And as water might encounter or come into contact with that fill, might it be problematic? So I'll pause there and then hand it off to another breakout group. I'll hand it off to Dolan.
Okay, yeah, thank you, Wendy. And thank you everybody in our breakout group. I think we had a very fruitful discussion. We actually didn't get beyond the building section. We spent a lot of time on the adaptation options for the built environment. But it kind of morphed into some of the same strategies that you would take for some of the open space and transportation utilities. So they're applicable, but we had a good discussion, really kind of focused on some of the elements of accommodating and adapting. So those include the dry and wet flood proofing and relocating critical utilities. Those are kind of the low-hanging fruit in these discussions of like things that we could be doing now and relatively easier to implement for existing buildings. We had some discussion about the distinction between new construction and adapting and renovating older buildings. Totally different approaches that you would take with those. And let's see, what else? We talked a little bit about the need to, really interesting comment that Justin brought up about if we're doing some of these accommodation strategies, wet and dry flood proofing, could we maybe just a thought, we need to consider how that might impact the building's resilience to other coastal hazards. Think tsunamis in particular. If you're dry flood proofing the basement or the ground floor, what does that do for tsunami impacts? So some interesting thoughts there. I can't say we came to any conclusions or resolution of what to do about that, but it's just something to think about with some of the sea level, or in this project is focused on sea level, but it obviously integrates in with some of these other coastal hazards and what we would do to adapt to those as well. I'll stop there.
Great, thank you, Dolan. And Chip.
Yeah, we had a great discussion. So fill is seen as the default approach, and basically everybody agreed that the default solution needs to be fill plus walls. A question: where would the fill come from? And then all the logistics associated with that, of course, are huge questions. As far as dry flood proofing, Rick pointed out that basically that's going on already today. There is, in his words, quote, a constant battle. And so if there's a constant battle today going on in the lower levels of the buildings in Waikiki, is that an indication that it's going to be a successful strategy in the future? We wouldn't want to continue something currently described as a constant battle. So it's an interim measure, it's a bridging measure, so to speak. Electrical and elevators, of course, are key in this. And then I learned a fun statistic that the Kalakaua Avenue is the third most important shopping location in the nation as far as the streets. You've got Fifth Avenue, Rodeo Drive, and Kalakaua Avenue. And so we also learned that any sort of a barrier to a shopper getting into a store is going to decrease sales. So that's one reason why you see, instead of individual doorways, so often you see on Kalakaua, just the whole front wall is gone, especially I'm personally thinking of the ABC stores. All designed, in fact, the street is designed to enhance shopper access. How do we maintain that in an era of adapting to sea level rise is a key issue that we should not lose sight of. There's a need, I'll just end with this, there's going to be a need, as we've heard in other workshops, with a very close coordination and staging between government sort of responsibilities, especially in the area of transportation, but also utilities, and then private owners and other stakeholders. The coordination and the logistics here are going to be key to the success or lack thereof when we look back at the end of the century to how we did, so to speak. All right, thank you.
Good points, everyone. Thank you.
Okay, these are the last survey questions. We are repeating a few questions we asked at the beginning of the survey. We want to see if your viewpoint has changed after seeing the presentations. So please bear with us, we're almost done. And remember to hit the submit button at the end of the survey. Mahalo.
Great, thanks, Eileen. So this concludes our workshop. Thank you very much on behalf of all of our hosts for joining us today. Your input is incredibly valued. We have a very knowledgeable group with us today. We're going to incorporate your input into our future renderings and do our best to depict a vibrant, flood resilient future Waikiki. And we look forward to sharing those with you in the future. So have a wonderful day, everyone. Bye.